Hello and welcome to day 2. We're going to look at volume of revolution, the idea that you have two curves and it's revolved in a three-dimensional shape around a certain axis. But before we get to that, I just want to look at this beginning question here. If you have time, plug it into your calculator and you'll get this shape. You'll see here we go from 0 to 1. The difference with this one, we talked about it a little bit last video, but we have this area to this area. And notice that the top curve and bottom curve then change. And so therefore, when we look at the actual area bounded, we're going to need to do this right here is 0.178. And so therefore, we're going to go from 0 to 1.78 of the top curve, 4 to the negative x, minus the bottom curve, 1/4 plus sine pi x. Plus from 0.178 to 1 of, I'm going to call this y2 and y1. So we're going to go y2 minus y1 dx. Knowing that you could put that in your calculator, I just let those be that. But just so you guys understand that when you have an intersection point where the top and bottom curve change, you do need to change, have two separate integrals. Okay, so now let's look at volume. So there's two different ideas here. One, we have a disk. The idea that you have a function bounded by the x-axis. We're going to rotate it around about the x-axis, and you can see going to this problem that there's no hole, it's just a disk, it's solid. Okay, and it creates a three-dimensional shape revolving around the x-axis. A washer, on the other hand, is where you have one curve and another curve rotated about the x-axis, but that there's a hole in the middle. Okay, and therefore you have the top curve minus the bottom curve. Another one here is this is rotated around the y-axis, rotated about the y-axis. And you can just see how it makes a different shape. It's rotated about the y-axis. What this is saying here, and just so you guys have an idea, is if I have the curve, this is not this problem, but if I have the curve y equals x squared and y equals x, we know that our 2 points that we are 1, 1. So if I'm looking at revolving this about the x-axis, then the only part that I want to actually revolve around is this part. So that's why I'm going to do top curve minus bottom curve. But what if I just take this slice right here and revolve it around? What shape am I making? Well, I'm making a circle. Okay? We know the area of a circle is pi r squared. Now our radius, the radius is the top minus the bottom. And so the volume of it is every single slice. Every slice that you have, all added up of that tiny circle. Believe that this is infinitesimally small. You're adding up all these circles that are being rotated, that are created by being rotated about the x-axis. All these circles up until the final point. And when you push them all together, you will get a three-dimensional shape. Well, to add up all those circles is the integral from a certain bound of the top curve minus the bottom curve. Yep. Squared with pi. We know that's pi r squared. I can put the pi out in front. I could have put it in the inside here, but you can bring it out in front because it's a constant. So you have the integral from 0 to 1 of pi r squared, the radius being the top curve minus the bottom curve. If there's not a top curve, or if there's only a top curve bounded by the x-axis, then it's just that function squared. This is pi times the radius being that function from a to b. So, just so you guys understand that. So now after my long-winded explanation, we'll look at the actual example here. Find the volume of a solid that is obtained when the region of y equals square root of x, I drew that over the interval 1 to 4. So if we are looking at that, it's just this area right here, is rotated around the x-axis. Notice that this is not a washer, that this is a disc. There is no hole. You're taking all of this and rotating around. So therefore, all it is the integral from, not 0, try again, try 1, to 4 of pi r, the radius which is square root of x, squared dx. Now, if I had to do this out by hand, I could go bring the pi out in front and just do x dx from 1 to 4. And so you're going to get x squared over 2 from 1 to 4. We're going to get 8 minus 1 half, which is 7 halves. So you're going to get 15 halves pi is the volume. Now, one thing I did want to show you was this idea of this curve, and I wanted to show you a three-dimensional type rotating around. So just take a minute and look at this. This is how it's rotated, and I'll scroll down. You can also see about the y-axis. So this is the rotating around the x-axis, the same curve. This is the same curve rotating around the y-axis. If this makes sense to you and you don't need to see this, skip over it. But I did want to make sure you guys understood what it looked like to rotate around. So for the next question, this is different because now we have 1 half plus x squared and g of x equals x. So take a minute and draw it out using your calculator. In my amazing drawing here, we're going to go from 0 to 2. I know it's an awful drawing. So we want to rotate that around. Notice that there is space down here. So this is a washer. So what we're going to do here is pi, the volume equals pi, from 0 to 2 of the top curve, 1 half plus x squared, minus g of x, minus x squared dx. Now again, the easiest way to do this is plug it into your calculator, y1, y2, and then do the actual math out. So the answer is approximately 6.9 pi. This would be units cubed. So why don't you guys look at this one. Actually, I'll do it because this is revolved around the y-axis. So again, we have y equals square root of x from x equals 0, bounded by x equals 0, and y equals 2. So we know that 2 is, the x value is 4. This is the point 4, 2. And if we're revolving it around the y-axis, you'll notice that it's going to go look like that. Look like the one that we had above in the picture here. Whenever it's revolved around the y-axis, we need to get in terms of y. If we're revolving around the y-axis, it's in terms of y. And so therefore, if that needs to get x by itself, this is x equals y squared. And our bounds are the y values. So in this case, we're going to go 0 to 2 of y squared, we still have the pi out in front, okay, dy. Again, using your calculator, just put it in terms of x. And when you do that, you're going to get approximately 6.4 pi units cubed. Okay, and for the last one, and the last one that we're going to look at has two functions that are rotating around the line y equals 2. There's the difference. We've always been rotating around the x-axis. This one's now y equals 2. So we have y equals x squared, square root of x. We know that we're rotating this area about this line. We're going to have a really large now hole of no matter in the middle. But that's okay. What's different about this is our radius now is looking, this is one radii, and this is the second radii. And so therefore the radius is now determined from the line y equals 2, and everyone has trouble with that. And so when we look at it, this radius is 2 minus that, and this radius will be 2 minus that curve. And so therefore, you're always going to look at the, quote, top curve is the longer radius. So we're still looking, our intersection points were 0 to 1. That's when they're equal. This is the point 1 comma 1. So we're looking from 0 to 1 of the longest radius, 2 minus square root of x squared. You need to make sure pi is out there. Minus the shorter radius, the green one, 2 minus x squared. Squared. Again, you would put that in your calculator and get approximately 1.033 pi. So again, how did we get this? This is the radius of the larger one. This is the larger radius. This is our smaller radius. How did we get it? Well, we looked at it and then we drew the radii in there. That's the key. If you do not draw the radius, it's much more difficult to see. So you need to draw the radii in there and then label it. Again, it's the larger radii squared minus the smaller, larger radius squared minus the smaller radius squared. And for the pun of the day, triangles and squares can agree on one thing. One thing they agree on is that circles are pointless. That was a good one. See you guys in class.